Hey everyone, let's take a look at one of the first murals you'll see as you enter the math hall at Walter Johnson High School. This mural, painted in spring 2025, displays the 5 Platonic solids. They're named after the Greek philosopher Plato, who believed these shapes were the building blocks of the universe. Each of these 5 solids is perfectly regular, meaning all faces are the same regular polygon, and the same number of faces meet at every vertex. There are only 5 convex solids that meet this definition. No matter how hard you try, you can't make a 6th one. The fact that there are only 5 Platonic solids comes as a surprise to many people. Regular polygons in the plane come in any number of sides. If you want a regular 23 gon, you can have it. So why are there only 5 regular solids? It might be surprising, but it's actually pretty easy to explain. If it's going to be regular, we're going to need to use regular polygons for the faces. So let's start with equilateral triangles. You need at least 3 to make a corner. And if you make this choice, you'll get the tetrahedron. If you choose to have 4 coming together at each vertex, you'll get the octahedron. And if you choose to have 5 coming together at each vertex, you'll get the icosahedron, which is 20 triangles coming together. What happens if you choose to have 6 triangles coming together at a vertex, though? You can try this. 6 equilateral triangles at a vertex ends up being flat. Did you figure that out? Here, look. Just to illustrate. Yeah, so that's not really a corner, and we're done with triangles, using triangles. If instead we try squares, again, we need at least 3 to make a corner. Can you picture what that would be? Making this choice gives us a hexahedron, or maybe you thought about it, it's just also normally called the cube. If we have 4 squares at a corner, well, we're already there. We're flat again. So we're done with squares, right? You get this. Let me get out of the way. There we go. So 3 squares is all that works. So let's move on to pentagons. We can choose to have 3 at a vertex, and if we do, we'll get the dodecahedron. There it is. Now, if we choose to have 4 at a vertex, it's worse than flat. They don't even fit. Got to get out of the way of this thing. They don't even fit. That's 4 108-degree angles. Can you do the math? Yeah. If we try to get a 4th one in there, you can't even fit. So we're done with pentagons. So what about hexagons? If we choose to place 3 hexagons, regular hexagons at a vertex, we're already flat. So hexagons won't form corners at all. Look. What about heptagons, that is 7-sided polygons? See if you can figure out why 3 at a vertex doesn't make sense. The same logic will apply for any regular polygons with a number of sides greater than 7. So we've got them all. These are the only 5 regular solids. To review, here are the 5 Platonic solids. The tetrahedron, which is 4 triangles, 3 at each vertex. The cube, which is 6 squares, 3 at each vertex. The octahedron, which is 8 triangles total, 4 coming together at each vertex. The dodecahedron, which is 12 pentagons, 3 coming together at each vertex. And the icosahedron, which is 20 triangles, and there are 5 coming together at each vertex. Now let's look at some properties of these beautiful shapes. First, how many vertices, edges, and faces does each one have? We can do some geometric reasoning to help us do this and take advantage of symmetry rather than counting by hand. For example, let's quickly count the number of vertices, edges, and faces on the icosahedron. First, we have 5 triangles coming together at this top vertex, and we could put our fingers on all 5 right there. And we have the same is true at this bottom opposite vertex down here. And then we have this middle strip going through the center here. And you'll notice that if there are 5 of these on top that I'm touching with this hand, then in this middle strip, we've got triangles that are joined along the edges, the 5 edges on this top. And so that means there are triangles, there are 5 of these like downward facing triangles coming from the top. And of course from the bottom we've got 5 that are kind of in that middle strip pointing upward as well. And now if you're keeping score, then what that means is we've got 5 and 5 on the top and bottom that I'm touching all 10 of those right now. And then we've got 5 pointing down here. Sorry, there. And there. These downward facing one. And then 5 pointing up. So if you're keeping score, that's 20 total. Now, if you know Greek, we already kind of gave it away. Icosa, this is the icosahedron. Icosa in Greek means 20. Now, what about the vertices? Well, each triangle has 3 vertices. There are 20 triangles, we just said. So that's 20 times 3. That's 60 total vertices, right? Well, not quite. If we do this, we'll have counted each vertex 5 times, since each vertex is shared by 5 different triangles. So the number 60 overcounts by a factor of 5. Therefore, there must be 12 vertices. That's so few that you probably could have just counted them by hand, right? We could have just put our fingers there, and then you can see there's 5 around the top, 5 there. So 12 total vertices. Last, let's look at the edges. There are 20 triangles, and we'll do the same kind of thing, right? And each triangle also has 3 edges. So again, that's 20 times 3 is 60 total edges, right? Well, again, not quite. Can you see how to correct this overcounting? Yeah, that's right. Each edge is shared by 2 triangles. This edge was counted in this triangle, but also in this triangle. So we have to divide by 2 to obtain 30 total edges. Now, you try this approach to count the number of vertices, edges, and faces in the other 4 Platonic solids. See if you can do it. Pause the video, and in a moment, I'll give away the answers. So, how did you do? I'm sure you did great. Now, take a moment to really look at this table. What do you notice? The first thing you might notice is that there are some numbers repeated in the table. For example, the cube and the octahedron have the same number of edges. If you had a pile of 12 sticks, you could choose to make either one. And you will also notice that the number of vertices and faces are flipped for these 2 solids. And now your mind is going all over. Look at the icosahedron and the dodecahedron. The number of vertices and edges correspond between them. There's something going on here. This is called the dual relationship. The cube and the octahedron are duals. The icosahedron and dodecahedron are duals. But what about the poor, lonely tetrahedron? What do you see? That's right, it's its own dual. The dual relationship is quite pretty. Let's take a look at the cube and the octahedron. For every vertex of the octahedron, there is a face on the cube. 6 for both. You can inscribe an octahedron inside a cube so that each vertex of the octahedron is placed at the center of one of the faces of the cube. Beautiful. It's also true that the cube can be placed inside the octahedron in a similar manner. Likewise, the icosahedron and dodecahedron can be placed inside one another, and the tetrahedron can be placed inside of itself. Let's take another look at that table. Pick a row and try computing the alternating sum at the bottom of the screen, and see what you notice. Go ahead and pause the video if you like. Do this for one row, or do them for all. And if you tried it, try a row, you'll get 2. I don't know which row you tried, but you got 2, didn't you? Now try another row. It turns out that this is true for every shape that doesn't have holes. Now we're getting into kind of some topology, really. So this is a property that's wonderful and special, not just for the regular polyhedra, but for any shape that's kind of sphere-like. This is called Euler's polyhedron formula. And the number 2 is called the Euler characteristic for anything that is ball-like. There is so much more we could say about the regular solids, but we'll stop there for now. Start looking for these as you go through life. You'll start to see them everywhere. They appear throughout mathematics, science, art, and engineering. For example, viruses often have icosahedral symmetry because it's efficient and stable. Crystals often form with octahedral or cubic structures, such as this octahedral fluorite crystal. Regular solids are perfect for creating fair dice. Many balls are shown using these patterns. Certain molecules reflect these geometries. And here's a Rubik's cube, or rather a Rubik's megaminx. You can see it's a dodecahedron. And you'll see these familiar shapes everywhere in art and engineering. These five shapes really are everywhere. And they were so beautiful to the Greeks that they associated them with the five classical elements: fire, earth, air, water, and ether. We chose earth tones for this mural, hoping we could capture that idea, that these are truly fundamental shapes. So next time you walk past this mural, remember that these aren't just cool 3D shapes. They're ancient, elemental, and mysteriously beautiful. Thanks for joining me on this journey, and we'll take a look at some more murals in the next one.